is James Kubli. I'm an applications engineer here at Saratech, and I primarily work with Femap using NX Nastran. In this video, we're going to be talking about doing a creep analysis using the basic nonlinear static analysis, also known as SOL106. That's packaged with your basic NX Nastran. We're going to be using an example out of one of the Nastran guides, the Nonlinear 106 NXN PDF file that you can find in your installation folder in the Nastran help. I'm going to switch over to this one over here. I've got it, what's the word I'm looking for? Oh, printed down to just a few pages so I don't accidentally scroll too far and get lost in the video. But as you can see here on the left, we are duplicating this model right here. This was one of my practice models. So we're going to be going over how to set up this model and use the material properties associated with the exercise 6.48. Now, unfortunately, not everything is fully defined in this model, like the material properties. It only mentions that it's stainless steel 304, but it doesn't give us the temperatures at 1100 degrees Fahrenheit. And for my experimentation, it definitely does not behave like this if you use 304's material properties at room temperature. So we'll have to make some minor corrections and some educated guesses. We won't exactly match the results here. I have some theories for that. We'll discuss it when we get to that point. But for the most part, the steps should be identical. We've got a material model. We've got our creep material model. We've got three functions fit to it: the A, R, and K. We won't be going over how to do the curve fit. Just after you've got your information here, how to input that into Nastran. Let's go ahead and start a new model here. I apologize for the large display here. Hopefully you have enough resolution to see it. It's just kind of difficult to show both the exercise and Femap at the same time. So let's go File, Import Geometry. This should be our model right here. We'll go ahead and accept the defaults here. And I just want to verify that we are using, that we did get the right dimensions in. Femap is unitless. And the translation could obviously be a source of problems here. Snap there, okay to there. Okay, so we should be looking for our delta Z right here. And matching that to here. So 2406 inches, and we get 24.05995. I'd say that's close enough. Looks like just a slight round off there. So let's jump into setting this up. First things first, we're going to define our materials. So according to the exercise, it's type 304 stainless. So we're just going to jump to that. Scroll down here. There is a type 304 in the Matte Engineering inch pound force. Material properties, it's near down the bottom, stainless steel 304, and we'll load that up here. So there we go. Now we've got our basic linear properties. Let's jump over to the creep tab and go over our setup here. So we're going to change this over to empirical model. We're going to throw in our reference temperature. It doesn't really have an effect on our analysis. I think it's just helpful for us to know. And now we're going to need to define our empirical creep law and its coefficients here. Femap has a funny way of displaying the functions that you're referencing. A, B, and D here are all constants. And when it has a single asterisk, that's a multiplication, but a double asterisk is a caret for an exponent. So keep that in mind there. It may not look exactly like what you're expecting, but it means the same thing. So like here, for example, we've got A times S to the power of B. So if we look over here, we got a constant here that's 6.985 times 10 to the negative 6. S here represents our sigma or our stress, We can see by the double asterisk that that is then to the power of b being another constant, that's our 2.444. And that basically all applies for our two other functions here. We can see c times e at being the exponent. So we got a constant times exponent time with a constant times stress. That matches our function here on the left. And then for k here, if we look at it, here we've got e. This is just another constant. It's not the exponent. Then we got sine at h. F, another constant, times s. So we can see here, sine of h, constant times our stress. And all that's raised up to the power of 3. So we're going to go ahead and just put that information there, starting at the top. That should be the 6.985 e to the negative 6. You just hit tab, go 2.444. Tab again should bring us to our next one. So we're just reading here from left to right, top to bottom. 7.032 e to the negative 4. That's 0.1072. Always double check that one. E, so we're at 6.73 e to the negative 9. Our next is 0.1479. And then lastly 3.0. Perfect, that seems to match out. And we are done defining our creep law and coefficients. Now I want to point out here that our stress and time are measured in KSI and hours. So we do need to make sure that the rest of our model matches KSI and hours. And if we go back to our linear properties here, we'll see that our Young's modulus is E, the 28 e to the 6, that's in PSI. So we do need to correct that. So let's just drop off 3 zeros there. That should now be in KSI. Now there's another problem here. We're pulling in material properties for 304 at ambient temperatures or room temperatures most likely. And that's one of the things that's going to throw off the results that we're trying to match here. This stiffness is too high. We won't see strain start off right away. So we're going to want to make a slight little correction to that. If we were to look at the previous exercise, this one, which is partially cut off, I didn't print all of it. Actually, I did. It should mention that it's using the same material, stainless steel 304. But if you dig into, yes, type 304, stainless steel 304, it doesn't provide the material properties here, like what the modulus of elasticity is doing. But if you go back to the main document that I stole this from, scroll all the way towards the end, somewhere in like chapter 11, you'll see that it actually has the Nastran deck file for this exercise here. And in there, it actually shows the material properties for the 304 it's using. And it's using 20,000 KSI instead of the 28. And it's also using a Poisson's of 0.3. So we're going to just adjust both of those there to match. Hopefully, it is an assumption that they're using that same material properties for this model here. We don't have to worry about anything else. None of those are going to play a part in our results at this moment. We don't have any acceleration, so our mass density isn't going to have any effect. And our limit stresses, we're not going to be calculating any of that, so we're not going to be concerned about that. So what we can do here is we can label this at 1100F, just so that we know what it is. And click OK and cancel. And with that, we've defined our creep material properties. So we'll go new. We're going to do plate elements. You can see here our shell thickness is 0.33. So I'll put this in here. We'll pull up our stainless steel. And we won't bother with the name. We'll click OK, cancel out of this. And then we're going to use the meshing toolbox to mesh this with. We're going to use map mesh. Be sure to change the property here. We want to adjust this to our plate property. Otherwise, if we were to go through and start meshing the model, it would create planar elements. And that would give us some problems in our analysis. So we'll click OK. We'll click on these 3 surfaces. We're just going to take advantage of symmetry here on the model. And there we go. We've got a mesh, but this is a bit on the coarse side. So let's just go ahead and like duplicate this mesh over here. Let's go to mesh sizing. We're going to set number, and I'm just going to count the number of elements. 5, 6, 7, 8, 9, 10, 11, 12. 12 there on the bottom. So I'm going to put this to 12. If you're on an older version of Femap, I believe this may say set 2 instead of set number, if I remember correctly. There we go. We did 12 there. This should be 1, 2, 3, 4, 5, 6, 7, 8, 9. Go there. If I remember correctly, that should be 5. And lastly, this edge here should be 8. So there we go. We're close. But you can see there's a bit of bias here on the mesh on the dome here towards the fillet. So let's go ahead and take care of that. So right now, see spacing is set to equal. Let's set that the bias to use pick location. And I'm going to click here. We can see it's a bit more biased, but from the image here on our right, it does look like it's a bit more biased than what we've got here. So I'm going to change this to 4 and just re-click. And there we go. I say that's close enough. If we do take a look here, it didn't apply the bias around, so the other side is unbiased. So let's go ahead and fix that. We'll click on that right up on that edge towards that end, and that should set our bias towards that end. And there we go. Now we have our mesh. So let's go and now define our loads and constraints. Let's just call this constraint. Okay, we only have one constraint. Unfortunately, I could not find anywhere in the model that tells me how this model is completely constrained. I'm going to assume that this edge is pinned. Call it pinned. We'll leave that to pinned. And then we'll do the symmetry here. Do a highlight. Okay, that looks right. Call this symmetry. There's no direct shortcut for symmetry on this curve, but this is TY. You can see from here, that's in the TY direction. So it's always TY, and then the other two rotational degrees of freedom. So now we got our constraints. Let's go ahead and define our loads. Now what we're going to do is we're going to break this up into multiple loads here because it is multiple loads. We're going to do this as multiple load sets, and we're going to use the load set combination to help make the subcase generation a bit easier. What we have to do when we set up the analysis is we're going to have to run a nonlinear static on 312 psi here. Then we run a creep analysis on that. Then we run a nonlinear static on the unloaded. Then we run a creep analysis on that. So we're going to end up setting quite a few subcases up. So I think this is a little quicker in setting up. I don't know, your miles may vary depending on your situation. But let's go ahead and count. We got 1, 2, 3, 4, 5, 6. So we've got 3 loading conditions and 3 unloading conditions. We're going to have 6. So yeah, I'm going to call this just first load. I'm going to call this 3112 psi or 312 psi. And let's go ahead and apply this on surface. Surface is there. Just highlight to verify. Okay. Now remember, because our creep material properties are in KSI, we need our loads, our PSI pressures to be in KSI too. So we're going to change this to KSI, which is going to be 0.312. I already know the elements direction or the normals are going to give a positive value reverse. So I'm going to just change it to negative so that we get our pressures outward instead of inward. And there we go. We're going to do a new load set. Call this the second load of 356.5 psi. And we're basically going to do the same thing on surface previous. give it a name, 0.3565 KSI. Again, negative 0.3565. Okay, you can see the display updated. Wonderful. New. And that we want that 349.5 PSI on surface. Previous. Okay. And this converts to 0.3495 KSI. Again, needs to be a negative value. We'll go okay. There we go. It's updated. Now, lastly, I'm going to create a load set that I'm going to call unloaded, and that's it. I'm not going to do anything with that load set. There's not going to be any loads because we want these unloaded here. So now we're going to pull up our data surface editor. Depends on where you might have this at. I have it set on the side here. If you turn on that one right there, data surface editor, it's another way to turn it on. You can always go to tools and turn on data surface editor if you don't already have it turned on. Here we go. But I'm going to turn it on for the moment, pin it here to make it easier. And we're going to go to drop down here and go to load set combination data surface. And again, I was counting this before. This is the number of initial rows that we're going to want. We're going to count this based off, we're going to create the number of load cases that we need. So we got 1, 2, 3, 4, 5, 6. Now remember, we also need to do a creep analysis on each analysis. So there'll be a nonlinear static and then followed by a creep, a nonlinear static followed by a creep. So we'll end up, since we got 6 loading conditions, we're going to have 6 creep analysis subcases. So we're going to need a total of 12 subcases. So I'm going to change this to 12 here. We're going to use all the different load sets and go OK. I do find this a little odd. This starts off with 0 to 11. So like the first time I did this, it's like, oh, wait, 11. What did I mess up? But no, that's it. It's just from 0 to 11. So we still got 12 rows here. So what we're going to want to do is we're going to want to define our first loads. So this is going to end up being subcase 1. So we're going to be running our first load, and then subcase 2 is going to be our creep, which is going to be, again, be our same first load. So we need to do a 1 and a 1. We always need to have the same loads and constraints applied for the subsequent creep analysis. So we do a 1, 1 there, and then our next is going to be an unloaded simulation. So we're going to do a 1, 1 there. Then we get to our second load, 1, 1. We get to our unloaded, 1, 1. Again, first analysis is the nonlinear static. Second analysis is the creep. 1, 1 for our final load of 349 PSI, and then our unloading simulation. So there we go. We've got, that's basically the different load conditions we're going to have. Again, our first subcase is just going to be the application of the first load. Our second subcase is going to be the same thing, application of the first load. But for the creep analysis, second subcase is unloaded, followed by the creep analysis. Third is our second load, or fourth, what is this, fifth? Sorry. Fifth one now. Our fifth subcase is going to be the nonlinear static for our second load. Our sixth analysis is going to be the creep, subsequent creep, and so forth from there. So now that we've got this defined, in order to create the load sets, we just need to right click and do create combined sets. You can go over here on the tree now and see that we've created all these different load set combinations. No, not really combinations. I'm just going to go ahead and delete these original ones, so that way when I get to the load set or the multi-set combination or for creating subcases, I don't have to deal with those original ones. I'm just going to renumber this just so it's all nice and clean. So there we go. 1, 2, 3, 4, 5, 6, all the way to 12. I'm going to unpin this now. So now we have all the different loads and constraints applied to our model. Let's turn those off just to make it a little visually cleaner. Now we just need to go to the analysis setup. We'll go new. Keep in mind that this is going to be a solution 106. I'm going to go down here. That should be option 10 here, the nonlinear static, which should be solution 106. I'm just going to click OK. We're going to go in and customize some of the options later, but right now I'm going to go to multi-set, and it's going to create all the different subcases I need. So all my loads are selected. The only constraint I have is selected. I'm going to click OK. And now I've basically got a combination of those and every subcase that's going to be needed. So let's go ahead and modify things. We're going to expand here, and we're going to go to the nonlinear options. This is under global requests and conditions. If I define the nonlinear options here, it's going to default to these options, and I can use this just as the default for all the nonlinear static subcases to use these options, and I don't have to modify the other subcase or modify those subcases. So I'm just going to click Edit here, and now we get to our nonlinear options. Here, we're going to set the number of increments or time steps. I'm just going to set this to 20. These analysis should run just fine with 20 increments. And then also I want to make sure the output control intermediate is just set to no. I don't really care about the intermediate results for each nonlinear static analysis because our concern is the creep analysis that we'll be doing. I'm going to go ahead and click next because I also want to define not boundary conditions, but I also want to define what the default or default results that I want to request. So I could turn on like forces here if I wanted to. If I wanted the GP forces, I'm going to disable that because that's going to slow down our analysis a little bit. But we could turn on like total strain, elastic strain, strain energy if we want, and go ahead and click OK. So that anytime we don't set output request or nonlinear options, it's going to default to these global options, which is great. This works just fine for the nonlinear statics, but we're going to have to go through and modify the subcases for the creep analysis, because unfortunately that's going to be slightly bit different for each one. So we're going to go here. We're going to select the nonlinear options. We're going to go Edit. Remember, every other one is going to be a creep analysis. So in this particular case, every subcase that's an even number will be our creep analysis. So when we get to our nonlinear analysis options here, we'll check the box for creep. We'll see we'll now have the options to time increment. And if we can then go over our plot, this is where we're going to refer our creep setup here. So it's not exact here. This kind of looks like this runs for 1, 2, 3, and maybe a third. So 333 hours. I'm going to put 333 in here. Now this is going to be a time increment. These units are going to be in hours. Remember, that is based off of our material properties, our creep material properties. They were in KSI in hours. So for simplicity's sakes, I'm just going to use one increment, so an hour increment. So it should give me 333 output sets just for this particular section of the creep analysis. And overall, we're going to end up with something like 1900 because I'm not going to quite do the math on some of these increments here, or these time frames. For simplicity, you may want to do the math just so you don't end up with that many output sets. That could definitely make your results file very large when models get much larger. But since this model is very simple, it shouldn't be much of an issue. Now, the other thing I want to point out here is output control. We do want to turn on intermediate output. By turning on yes, so that means we're going to get all of these 333 increments for this particular subcase. If you set this to all, it'll give you any sort of intermediate ones. If it struggled to converge and it had to cut the increment down, if you turn on all, you can get those intermediate results on, but we don't really need that. because we definitely have enough fidelity with 333 increments. Unfortunately, this output every nth step is not available in this analysis. I wish it would. Otherwise, we'd be able to just stick with this time increment in this, and I could tell it to give me every third result, bringing down the number of output sets that I'd have. But no, it's not available. I'm going to go ahead and click OK. We don't need to worry about the boundary conditions. Those were, if we click next here, we can see they're automatically set. That's a nice thing about using the multi-set. And we don't need to go in the output request because we already defined those for our global. So now we just need to define the other ones. So give me a moment here as I go through this. It's going to be every even one. Change this to creep. It looks about 166. Not 99. Hour. Change this to yes and go OK. Jump to 6 here. Edit. That will be creep. Let's see here. We've got 1, 2, 3, and I have no idea what that is. Again, is that looks slightly bigger than a third? So 1, 2, 3. I want to say that's 40 hours there. So 340. Not 14. We'll go 1. Yes. Click OK. That was 6. Now we want to go to 8. So that should be 60, 1, 2, what is that? 90 maybe? So 60 plus 90, that's 150, 1, 2. So that's roughly 350. Let's see, you have to do a best guess here, which makes things a little difficult. So who knows how accurate we're going to be. Yes, we'll go OK. So if we say that was 10, then we'll go 110, 210, 310, plus what, 5, 315. So go edit this one. Creep, change this to 315. 1. Change this to yes. We'll go OK. Now we're on to our last one. Oops, I edited it too soon. I didn't click on the nonlinear options, but that's fine. So if that's 95, 1, 2, 3, so 395 for an hour each increment. We click yes here and click OK. So we should, in theory, end up with 1906 results, output sets. And we'll have the 1900 for the creep, and then we'll have 6 for each of the nonlinear static output sets. So that there should be everything we need to set up the analysis. We now should be able to just click run and go. So I'm going to just click analyze here. Give it a moment. Looks like everything translated okay. No error messages there. We'll go over the nonlinear history. You see it's marching along just fine. We're only ever going to see the positive subcases, or the not positive, but the even subcases, the creep, due to the number of increments it's got to take. The nonlinear static solves so quickly that we won't actually see it. There's no way to go back and forth here. So this is going to take a couple of minutes to run. So the analysis has completed. All the subcases are done. We have solved. We can see down here in the message window, we've got 1906 output sets. So let's go ahead and review our results. We'll close that down right now, and let's bring up our post-processing here. We could turn on deform, contour. I find that deform's a bit weird with this model based off the exaggeration. So I usually like to modify the scale a little bit and set that to like 5%. Come on. Is that still, there we go. So yeah, still a bit interesting. So let's just turn off that anyways. So there we go. We were looking at our plate top von Mises stress. We're looking at the very last output set. Let's change that to strain here, for example, because we're really concerned about strain. We're just going to look at von Mises, not stress. We want von Mises strain. There we go. All right, and according to the graphic, the gauge location is what? Right here, maybe? So let's see what our results look like. I mean, this is just our final strain value on the very last output increment. So that'd be somewhere around our 1900 hours. Let's see that somewhere around right here. You can see our results don't quite seem to match up. They're getting a strain value of 2 point something, e to the -3, and we're like a whole order of magnitude off at 3.5 e to the -4. So again, I haven't been able to fully figure it out. My best guess right now might be this particular wording right here. It says total circumferential strain versus a single element strain. So that might be the reason why it's not giving us the exactly same results. But let's go ahead and take a look at our charting, because we can at least verify if our strain is behaving like the graphic here. So I'm going to pull up charting here. I'm just going to pin this down so we can see it. New data series. All right, and we're going to just call this strain, and we're going to be using vector versus set. Right now we could use all output sets, because that's literally the only results we have are for this one creep simulation here. We'll change this to von Mises strain. On our location, let's zoom in. We want that one there. Go highlight, perfect, and go OK. And we'll click cancel that because we don't need another one. And here's our plot. So you can see, for the most part, it does seem to behave nearly identical. We could see the slope here, the curve, and then after unloading, we get a relief in the strain. Then a new loading ramps up. We see an increase in strain. Again, as it unloads, we see it decrease over time and then ramp up. So we're very similar, but again, we are still slightly bit off. We can see our peak strain here is 0.0065. This is also the von Mises strain. If we used the circumferential, or probably the best thing to do would be use like the cylindrical coordinate system and look at the y strain rate. And then maybe if we got one value here and multiplied it by the number of elements we've got, or multiply it, because that would be just summing up those number of elements, would probably give us closer results. But again, it's hard to tell because of the fact I've had to make some educated guesses on what the actual material properties were, because they're not explicitly given. The constraints are not explicitly given, so I've had to make those up. I've played around with the constraints to see if they had any effect. They did not, so they did not seem to make any sort of difference in the strain right here. So I'm not 100% sure why we don't match it exactly, but the reason I picked this exercise is because it was a bit more complicated in that we had multiple loading situations. So this did make things a little bit more complex in defining the setup here. And I just wanted to go over that, especially if you had multiple loading conditions. Otherwise, if you just have one loading condition, it's just two subcases. You get your nonlinear static followed by your creep analysis, and that would be it. Well, thank you for joining us for this video. Hopefully you learned something. And check us out, follow us out for some additional videos that will go over some more stuff that you can do in the nonlinear static. Thanks.